Thank you very much for this opportunity to show some results from some numerical models that I've been doing in Potsdam, together with all these people shown here. So Sasha Bruna, Anna Glerium, Dylan Vezi, John Nalibov, Jan Retematschel, and Eric Gaucher. And we are interested in the natural hydrogen potential in rift basins and also in inverted rift basins. And these are some results that are already shown here in this slide. So the reason that I started this project is that we are trying to realize the energy transition, and we want to move away from carbon fossil fuels. And hydrogen gas seems to be a very nice means of getting energy. And if you burn hydrogen, you only get water and energy, so that's very clean. But there is a big problem with this, is that we need to still produce this hydrogen somehow. So we need to put energy in there. So it's either very polluting or costly to get hydrogen. There are different ways of classifying it, like gray or blue or green hydrogen. But in either case, wherever the source of energy and how you do it, it's still going to take a lot of energy. So that's not really great. But there might be a different solution, and we've already seen this in the last talk, but substantiation might be a great way of producing lots of hydrogen from the earth. So in a free way, if you want. So we just need some mantle rocks with some minerals like olivine and pyroxene, some water to produce serpentine, and maybe some other reaction products. It's not as simple as shown here, and we get hydrogen. But then problem is, of course, yeah, we need to get the water to that mantle rock. And if you look at a cross section of the Earth, this mantle rock is often at something like 30 kilometers below the crust. So how do we do that? And in the last talk, we already saw that we can simply start a rift, and we can start to hyperextend margins and get this mantle close to the surface where it can react with water and produce lots of hydrogen. But there is another way as well. If you close a basin like this again, you can have pieces of mantle that are being incorporated into an origin, into a mountain range, and there they can also serpentinize. And we know that there are some studies that have shown that natural hydrogen seems to be available in these kind of environments, but we just don't really know that much about this. So there are these two systems, and we need to really study and get a better idea about what is going on. So I started to do numerical tectonic models in Potsdam. And I'm using Aspect and coupled with Fastscape. So Aspect is a geodynamic code. Fastscape is, as you can see here, for surface modeling, and this would be the Aspect code. And I'm taking just a simple rifting model from Neuhardt et al. From 2022, where they did rifting. And the great thing is there that you can do stuff like temperature and surface processes, which are really important. And I simply was able to, instead of doing only rifting, I could also invert this process and do compression and get my inverted basins or basin inversion. And a model might look a little bit like this, where you start to rift first, you get a basin, you can see how the mantle starts to rise to the surface in your rift, or in your ocean even. Then we might have a little tectonic break, or a tectonic quiescence if you want, a pause, and then we can start to close it again. And maybe I forgot to kind of say, but this is the crust, and all the green is the mantle. So this is the lithospheric mantle and the asthenospheric mantle. And importantly, we get pieces of mantle that are taken into this origin and remain close to the surface. So that's very important. That's what we are interested in, next to whatever happens in the rift. So we can clearly show that in these models and in this kind of systems, we have mantle exhumation, which can be defined by the amount of mantle above this dotted line here, which would be the base of the crust at the start. So you can define that mantle would be any mantle that's exhumed. That's the mantle, that's the green stuff below this line. That happens in a rift system, but also during inversion. So you can have a piece of mantle, but we're not there yet. We need to understand where the hydrogen is. And so therefore, well, first of all, we need this exhumed mantle, but we also need the right temperature, water, and to make this all happen. So we were basing ourselves on the previous work, or the work that was previously shown in the previous presentation from the analog model, the numerical modeling by Liu et al., where we assume that subtonization is very efficient between about 200 to 350 degrees centigrade, which is the subtonization window. There is where that's a temperature where the subtonization really produces in a quick time, in a short time, as much as hydrogen as possible. And then we need to get that water there. So in a similar way, we assume that we need large faults, like are shown over here, which are active so that they are actively being opened and water can flow through. And if we put that all together in this picture over here, we have this mantle that gets to the surface. We have a temperature window here in this turquoise color. And then we have in black, we have our shear zones that go through the mantle, and yellow part, that's the part of the shear zones that is in the mantle. So that's the area that would be subtonizing and producing all the hydrogen. And that's what we're looking for. Well, we can do an analysis of our models, and it would look a little bit like this, where you have your rift again. The mantle gets to the surface. Sorry, and by the way, this is the subtonization window. You can see it gets very thin, actually, in the rift, and we get a little bit of yellowish dots there. That's why the subtonization would be happening. This is a tectonic pause. Here we can see that the whole system is cooling down, and therefore the window starts to become larger. And then we start to compress again. And here you can see there are large pieces or large areas that are yellow. That's where the subtonization would be happening in an origin. So if we do it maybe once more, you can get an impression of how much subtonization we could expect in a 2D section, which is very small in a rift compared to what you can get in an origin. So here it starts to compress again, and we get these large pieces of yellow, which is really the place that we are looking for. So then I can show you a couple of key models to get a bit of an idea of how the system works and what is important. So this is a model here where we have very limited rifting at the start. So you can see there's only a very limited amount of exhumed mantle. And then if we start to compress again, we invert this basin, you get just a system where there is almost no mantle close to the surface. So it's not really interesting. There is no mantle really in the temperature window. So it's not really great for what we want. However, if we start to rift for a bit longer, so this would be 50 million years of rifting compared to the 5 million years before, we get mantle exhumation towards the surface. And if we do a zoom in here, you can see there are these yellow dots. That's where the subtonization would be happening. So that could be your North Atlantic if you want. And then if we start to close again, then we have the bigger pieces or the bigger areas of subtonization that we saw in the video before. And this system then continues, and we get an asymmetric system that might remind you a little bit of the Pyrenees or the Alps, something like that. Interestingly, this is what I showed you before in the video as well, is that the subtonization window, which is shown in this color, it's very thin during the rifting, but if you let the system cool down, then because it's a temperature window, the system cools down, the window becomes larger. But as there is no deformation going on in tectonic pause, in the post-rift, post-cooling kind of environment, we don't expect much subtonization going on. So there's no yellowish areas there. And then there is a last model in which we have more extension. So 25 million years of extension. You can maybe consider this an oceanic rifting phase in the end. And still here we have very small areas of subtonization compared to what we can get during our origin, where we have larger areas of yellow, let's say. So that is an important take-home message, is that we need large amounts of rifting, but if we then close the basin again, when we can actually get more stuff. So we can also plot things like, for instance, the amount of exhumed mantle. So that would be the amount of mantle that gets above that original base of the crust. And this is the first model, this is the second model, and this is the third model, in which we have 5 million years, 15 or 25 million years of rifting. And what you can see in this dark blue line is that we have a steep increase of mantle exhumation, which increases linearly up to a certain point. So it keeps on increasing. So even more and more mantle gets to the surface during rifting. But at some point there is also what we can see here in this other line, this bright blue line, is that not all the mantle is actually moving upward all the time. So it's not that the mantle just keeps on rising all the time, but there are pieces of mantle that are moving up and down. So it's quite a dynamic system, which is an interesting observation, I think. Then if we start to cool the whole system, a bit of the whole system starts to sink a little bit. So there are sediments covering the area, the basin. So we get a little bit of less mantle exhumation or exhumed mantle. And then if we start to compress the whole system, you can see that the blue line here goes down quite a lot. And almost all the mantle goes down again. But it's important to realize that in certain areas, or in certain models at least, we get still a piece of mantle that remains within this origin, and that's very important for the hydrogen potential in these kind of environments. And then we also can plot the size of our subtitization window, which also increases over time if you cool down. That's what we saw in the video, and it becomes larger and larger as more mantle is being exhumed. So it's a very, very simple way of looking at this. But we can do more with this.
11 minutes.
11 minutes. Okay, excellent. Almost there. So then what we can also calculate similarly to what was shown before in the previous talk, in black here on a logarithmic scale, we can plot how much subtitization is going on, and which can be directly translated to the amount of hydrogen that you can expect. So if there's very little rifting, we might have a little bit of hydrogen or subtitization going on, but not very much. If we do more rifting, then we get to a certain point here, this level R, and that's quite substantial. So that's quite good. However, if we then keep on rifting, this remains a bit of a threshold. So there is kind of an upper limit due to the geometry of the system, the size of your subtitization window. But if we then go into compression, so that would be this line here, and this line here, you can see that that line is substantially higher, about 20 times higher than what we can get over here. And if you look at this red line, this is the cumulative amount of subtitization or hydrogen production that really starts to kick in when we start to have inversion. So the inversion phase seems to be very interesting. So we can put this all together in a bit of an overview in which we see that if we start to rift, we start from the pre-rift to early rifting, more advanced rifting, and then into the post-rift cooling phase. The yellowish bubbles here, they show the amount of hydrogen that's being produced. So we need to get to this stage to produce hydrogen. During the cooling phase, there is no production in principle. And then if we start to invert, then we want to get into a system like this where we have a piece of mantle that is being pushed up into the origin. And this can be plotted in the different tracks or pathways that we have here. They can be plotted in this graph very simply. But one thing that we didn't talk about yet is that we also need reservoirs and seals if we want to have, let's say, something like a field of hydrogen that we can drill. So we need to think about something like a hydrogen system where we have all the different components that are active or present at the right time to produce like petroleum, like oil and gas. We can have fields of hydrogen, hopefully. So this would be an orogenic hydrogen system concept in which we have sediments that can produce the reservoirs. There can be also seals in there. We have our kitchen, if you want, where the hydrogen is being produced. We have faults that can allow migration of hydrogen to these fields, and then potentially we can drill this. And this is something that we need to develop in, for instance, the Pyrenees. People are thinking about this, but it's very important to consider the whole system, the whole hydrogen system, if you want. And then we can think about where to explore. This is just a little graph that shows a couple of potential areas, some sections. And it's very clear that from different inverted basins, we need a certain amount of rifting before we can get the mantle to the surface. So stuff like the Atlas or maybe the Caucasus, they don't seem to be very promising, but the Pyrenees, they look pretty nice. We have pieces of mantle up there. So we need to study that. And also the Alps and, for instance, the Ronda peridotite in Spain. And there might be many other places like in Albania or Kosovo. Recently, there have been some publications. So the conclusions here would be that we need to exhume mantle for our hydrogen, but we also need water and reservoirs. So we need to really understand this kind of system, this kind of hydrogen system analysis approach is necessary. And we need to explore then these rift inversion origins, maybe better than rifts, because we have all kinds of options there. and reservoirs available. There seems to be plenty of potential in the Mediterranean that we need to develop. And if you want to know more, you can have a look at that preprint that we put out, and we're still working on finalizing the paper. Thank you very much.
Thank you very much, Frank. It was a very nice presentation. Thank you. I have a question, but I see that Nicolas Muller has asked questions in the chat. Would you like to discuss, to open the discussion, Nicolas?
Yeah. Living in Norway, and we have the Caledonian origin, which was kind of reactivated during the Atlantic opening, and we still have the crust moving, and we have shear zones. We have reactivated earlier thrusts as new shear zones, which are active today. So the whole picture gets quite complicated with respect to serpentinization and also hydrogen generation. And I think if we want to approach this or approximate this, we have to try to start 3D modeling. That's my comment.
Is that a comment to me? Sorry, I'm just...
Yeah.
Okay, yeah, absolutely. I mean, this is a 2D approach. It's a first order approach, if you want. But indeed, if we already look at the Pyrenees, for instance, or the Alps, there are clear 3D components to these origins, and we need to really understand the whole system in 3D if we really want to start to, let's say, put a drill hole somewhere and drill into a potential reservoir. So this is a very first order approach to kind of explore what might be possible, and many more different studies are necessary to make this a reality. So we're not there yet, but it looks quite...
If you use these numbers, they are used immediately by managers, and they say, oh, that's too low rates, and so on. And so be careful. It's just numbers based on simplified models. So that's not maybe what we can expect.
There might be all kinds of different factors that are coming into play. For instance, the type of mantle, like was already shown before, or the amount of the availability of water. It might be different, the hydrology.
In Norway, eclogrites are kind of formed by hydration of granulates. So this is a completely different process, and it has to be included too. So there is a lot of complexity here which we have to address.